Okay, so we're going to continue talking about the R scripts and RQTL stuff. Last week, we were working on going through that the script that converts the LetMap data files into an RQTL file. And some important points were setting the path correctly, making sure all the names of the LetMap outputs matched the information provided in the header of that document, making sure the file only contains a single VCF file, and eventually a phenotype file should be also in that folder, and it needs to have the word pheno in the name. And it's important to have all of the different packages both installed and loaded that are required for the script.
You mean every upgrade P?
Huh?
You mean a P particular unit?
I defined it that way, but I think I've realized it doesn't have to be uppercase pheno. I still put that because that's how I typed it in. So if there's any issues with that, that would be a good thing to try if it's not uppercase. Let's see, we'll go back to where we were in that script. I'm going to try to go through it a little more quickly today. Let's see, this is a script that we were on. Can you guys see that all right? And we were right here at line 74.
It's possible to enlarge a little bit.
Yeah, I can. Is that good? Okay. And so with this step, we were just we were labeling all the linkage groups with a number between 20 and 50 or 20 and 39, I think.
Could you please go up a couple lines ahead? I start 67. So could you take one little bit here?
On line 67. Okay, let me remember. Marker order. I should run some of this. 67. Okay, so marker order file is that file that has all of the marker positions and chromosomes along with the list number that we reference for the other files that come out of LetMap. In this line 67, I believe we're matching, let me open up subgeno. We're matching the marker number in this column. We're matching that to the number in the marker order file, which is this one. In this file, we're matching this column, the marker column, and this column, the third column. So if we go down to whatever this is, 429, whatever is in row 429 in the other file, we're copying that information and putting it in here because that's what marker this is referring to. And this line is just doing marker order 3. So that was the third column in that marker order file. Which one of those is equal to this subgeno for every single row in column 1, and it matches. And then you extract the information from the marker order file and put it into columns 5 and 6 in the subgeno file. I think this should be a J. Okay, and then after we've matched, we have to actually get the real names, because at this stage, we just have the chromosome in the physical position. which some of these, I think this is, how many observations do we have? This is GBS plus SSR. So some of these markers will actually be SSR markers with like real names rather than just the concatenation of chromosome and physical position. And so going into subgeno, we make sure on line 71 and 72 that the second and fifth columns are numeric. So second, this one, we just want to make sure that's a number, and fifth, we want to make sure those are both numeric so they match or not match, so we can handle them correctly.
So with this, we be able to handle SSR included.
Yeah, that's what's getting written right now.
SSR, we can use the physical position to represent.
Yes, when we convert SSR into the HapMap/VCF, you have to provide a physical position, and that's what we're referencing right now. We will be extracting the names because even sometimes, I think the GBS markers are always the same, but even like the ramp-seq markers, sometimes the physical position provided isn't the same, like identical to the name. Sometimes it's a few base pairs off since those represent segments rather than single loci positions. Okay, so rows or line 73, we're just assigning a group number to all of the different linkage groups, and we're differentiating between the groups. No, that's not what we're doing, sorry. 74, we are going through all the different groups. So we've already assigned a group number that's 20 through, I think 38, to all of the different linkage groups. And at this stage, we're converting those linkage group numbers from the 20 through 38 back to their correct chromosome number. So 1 through 19. And this is creating a list of the different linkage groups. So all of the different, within this subgeno file, all of the different markers which belong to linkage group K, and this K is just being defined as 20 and then 21 and then 22. It goes through and does it for all of the numbers in this range. Just a 38, so it makes more sense. And it's extracting column 5 from subgeno, so column 5, this one. And then we're going to use this column to reassign the chromosome to the true chromosome. But we can't just always take the first one, because sometimes incorrect markers get sorted to linkage groups, or markers get sorted to incorrect linkage groups occasionally, or sometimes 2 linkage groups get put together. So we want to take the chromosome which represents the largest number of markers in that group.
So in this step, this is the linkage number or chromosome.
Okay, so if I run this, we'll change K to 20. So we'll do chromosome or linkage group 20 at this step. This linkage group list is just, I think this gets stored as a list. It's telling us that all of the markers that are contained within linkage group 20, they all have a like physical chromosome or a true chromosome. They all they've all been mapped to that chromosome 3. And so this one, what the script actually does is it takes this list, and this list comes from running oh, I highlighted the wrong, sorry. We're down here. Subgeno, we'll do the whole. that list of threes just comes from subsetting all of the markers that have this linkage group 20. And so we can see they all have 20s and they all have 3s in this 5th column. And that's where that list comes from. And then in this step, we're sorting the list numerically. So if there would be, I'll add a 5 to the list. Okay, so now when I show you the linkage group list, there's a 5 right here at the beginning. And if we had the idea just to take the first number, we would get the incorrect linkage group. So what the sort does is it sorts it numerically or alphabetically. So now the 5 should be at the end. And we can see down here at the end, there's the 5 now. And what this step is doing on row 78, we're finding the median, which I could just rename this. I'm taking the marker in the middle of that list and using it as the chromosome to assign. Huh? I was just showing how it sorts it in case incorrect markers sort to incorrect groups, in case there'd be a marker that actually belonged to chromosome 5. We can't just take the one at the beginning. Instead, I like to take the median, since that one probably represents the largest marker group. So that's lines 74 through 79. I'll undo this. Okay. Okay, and then 80 is just concatenating columns 5 and 6 from that subgeno file or some subgeno object. And that was just chromosome number and physical position. And that's assigning it to a 7th column. So then we can reference both chromosome and physical position at the same time when we're looking for it from within the VCF file. Oops. So now the subgeno has this 5th column that looks more similar to what we do when we do this in Excel. Okay, so then previously we had imported that VCF file that we used for linkage mapping. And right now we're going to subset it just to get the first 3 rows, the first 3 columns. And the first 3 columns contain the chromosome number, the physical position, just like our actual map list. And then this is the ID. So that for the GBS markers, it looks very similar to what concatenating them does. It just has an extra S on the beginning. But if we get to like some SSR markers, we see that the real names are in this ID column. And we'll just be making sure all of these are stored as numerics and for the numbers, and making sure that the names are stored as characters instead of numbers. And then on line 87,
What's the age?
that's just, we looked at that yesterday, how the VCF file gets imported.
Okay.
It has different subsets of data. So there's the metadata, which is the header in the VCF file that has all those pound signs. The fixed data are the first 3 columns. And then the GT is the actual genotype data. It just stores those separately within this VCF object so that you can access them separately, more easily.
So this won't be done until you have the VCFR package.
Yeah, the VCFR package has to be loaded, which that's up here. I did that at the beginning. Let's see, okay. So line 87, we're just pasting to concatenate those again. So if we go back here and we've added a fourth column and it's concatenating these first two columns. And so most of them look very similar, but the SSR, like the SSR, now we have the chromosome and physical position to match to the last column in our map object. And that's all we'll do in here is match it. There's some extra stuff in case for some reason there's duplicate positions. It stores it to a file so we can check that later, but usually that's not a problem. So now the subgeno should have an 8th column here, and we've matched this column in the subgeno file and this column in the VCF file, and we've extracted the ID for the matching information, and we've stored it back in this 8th column of the subgeno file. And see, now we have the actual names of the SSR markers that match up with the map data. Like within one row, this is all for the same marker. So eventually we'll move this marker name back to the marker column and get rid of this other stuff. These are just writing the files in case there are duplicate names. I'm getting errors because there's not duplicate names, but that's what we want. Replace the names. All I'm doing is taking the subgeno file that we were looking, or subgeno object, this object that we were looking at. I'm taking out columns 8, 2, and 3, and those are the only ones that I want to keep because that has marker name, the chromosome, and the position on the centimorgan position from the map. And I'm storing it back to our original genotype file in columns 1 through 3. And the original genotype file, it had this information, and then it had all of the genotypes for the individuals to go along for those different markers. This stuff is just renaming the individuals because in the genotype file along the header, we still just have P1 for parent 1, P2 for parent 2, C1, 2, 3 for the individuals in the population. For this file, it would be like Norton, Cabernet Sauvignon, and cross CS 1, 2, 3, and so on. And that's extracting the information from the pedigree because the headers match the pedigree since it's all coming from LabMap, and that's what LabMap uses. Okay, these steps reorder the map because right now the map is just in the order that it comes out of LabMap. And so we get chromosome 5 first because it's the largest chromosome. And additionally, chromosome 5 looks like it has the smaller numbers at the beginning, but let's go to the next one and see if that's also true. Okay, 6. Most of the 19 chromosomes only go up to between like how many zeros is there? 25 to 35 million. Is that million? Yeah, million base pairs. And so these ones that start out with 23 followed by 6 other digits, that's probably the end of the chromosome, even though we're at 0 right here. And so this chromosome 6 should be flipped instead of, and these markers should come at the end instead of the beginning. And that's what this is doing.
You need to write the script to flip that.
Yeah, that's what this script does. It's just faster than doing it itself. And then that has created a new map, and we're going to replace the new map and match all the genotype information back into our genotype file so everything is correct. So now the genotype file has chromosome 1 through 19. The smallest end of 1 comes first to the largest for all of the different chromosomes. So that stuff gets written to some files. This step is starting to recode. It's just selecting the relevant columns, which we need for converting to RQTL style. And then this step takes the 1s and 2s genotypes, which LetMap 3 uses, and is converting them to the single number genotypes, which RQTL uses. And these are just all of in this first parentheses column, these are just all of the different possible genotypes which come out of LetMap. And this is just the corresponding genotype that's equivalent for the RQTL. And it goes through all of the columns and replaces it. That's writing the phenotypes to a file. And this is mapping, so make the map larger. Okay, and then this is the final map. I don't know why this is kind of blurry, but we can see that all of the chromosomes are ordered smallest to largest, so it looks pretty ordered or pretty uniform in that manner. And once again, this plot is just centimorgans across the bottom and physical position and base pairs across the y-axis. And so we can compare how well the linkage mapping estimated the position using the physical position.
This is only female only, right?
I was using a concatenated map, so it is the female column. They're the same for a concatenated map, but if you did the non-sex average maps, you can just go in.
So if we just select 0, then it's both of them at the same time.
No, I think it's the opposite, because in LetMap there's a parameter that's like sex averaged equals, if you put 1, then it is sex average. If you put a 0, then it's separate male and female maps. But what I was saying, if we wanted the male map, we could just come into this graphing instruction and change the X. This is the header of the female map column. That's female POS for position. We could just change it to male POS, and it would do the male one, which these will look the same since they're, yeah, these look the same. But if you did not do the separate male and female maps, you could just change it there and see both of them.
So you have to choose one is separate and then connect them together, or you have to do the male and female separate, and then you can.
This script handles both the male and female because like the markers sequentially, like they don't get mixed up at all between the male and female map. It's just the centimorgan positions are different values, but the order is all the same.
So if you use like 179,
Mm-hmm.
if you try not separate both of them, so what would you do for the position?
If you do want to keep them separate,
Not a separate,
not separate,
they're together.
So
these maps are exactly the same if they aren't separated. It just stores 2 columns because that's how LetMap formats everything, but they're exactly the same. So you can use either of them because they're both just sex averaged.
So you mean the consensus map? How you from to make construct consensus map?
Oh, and the consensus map is made in LutMap. You have to specify that in the parameters. You can't just like make separate parental maps and then you can't use that same map and convert it to the consensus map. You just have to run it twice. You have to run LutMap twice to get both the consensus map and a parental map. Does that make sense?
Right? Asking the right thing.
Yeah.
You want to do consensus, right? So from here, this is your raw data for the female and male
Mhm.
map, right? So how you run the consensus?
This is a consensus map. The headers still say male and female, but all of the numbers in both of those columns are exactly the same because I ran it as a consensus map in LutMap.
So, but as you say, every single one is identical
Yeah.
here, right? So that means,
You can just change the header and say consensus map because it is a consensus map.
but then this is just the map with the whole thing are identical. Usually consensus map, some of them from male, some of them from female still combined together, is that right?
Yeah.
Yeah, but this one.
When you
is
run the
all
parental map
identical.
separately, like there'll be like some chunks of markers that are all the same centimorgan because those are all informative for just one parent. And so it can't map different positions for the second parent. And so the second parent's column will all just be the same number. But when it does the consensus map, it
So to me,
estimates.
what the consensus map is the two parental map combined together.
Yeah.
So they still have some markers, was it from Norton, some markers. from
Yeah.
Cabernet Sauvignon. But in this case, they are identical. Am I right? Are they all identical? That's.
I guess maybe how I'm referring to it as consensus map isn't the same. Because it doesn't.
Because this one, correct me if I'm wrong, so this one actually you select Norton and Cabernet Sauvignon. Both had the same, the identical markers and then you combine together, so it's actually, so this is basically still Norton or Cabernet Sauvignon map, but you also could combine it together because they are all identical. Am I right?
So all of these, like, especially for GBS, like they're only informative for one of the parents. And what it does when it does the sex averaged map is it considers the like recombinations from like several markers to, I don't know if I'm explaiing this 100%
Because,
correctly.
for example, 1663, okay, that's one number there,
Mhm.
21 million. Is that at the same location of the Norton and Cabernet Sauvignon? You have the same marker.
This SNP marker would only be informative probably for one of them. I couldn't,
So it's informative on one, but not the other.
yeah,
So that one, when you combine together, well, this is still a difference. So now I understand.
Yeah.
So usually for SSR, if we have a map, some of them only specific to Norton,
Mhm.
some of them specific.
That's still
to
true.
Cabernet Sauvignon, right?
Mhm.
When they combine together, well, still there. But in your case, well, it's all identical, but some of them polymorphic to Norton,
Mhm.
some of them only polymorphic to Cabernet.
Yeah, and
Sauvignon.
when I'm
So
saying,
there's another sense of the consensus. Okay.
yeah, because when I'm saying average, like I really mean averaged, it it doesn't print out, but it kind of computes like male and female, and then it averages them together to give us one single version.
So in that case, it's not exactly male and female, instead it should be equal.
Yeah, it just it only has one file version, so it doesn't make like a different version for the average mapped versus the non-averaged maps. The file just prints out both male and female and it's the same. Because we need the two separate columns when it does the non-average, the parental maps. We don't need it now since they're the same, but it still just follows the same file format coming out of LabMap.
So again, correct me if I'm wrong, so this is the still VCF file, right?
No.
Actually, in LabMap.
This is a preliminary RQTL file, how it's stored right here. We've extracted, actually, it is more similar right now how it's pictured because it still says the 1s and 2s to the file that comes out of LabMap, the final output file. We've just converted the marker reference numbers into names now.
So I got a question. So this one is SSR with the GBS
Mhm.
right? So what do you think for application use? If we do, well, right now we have this combined together and use RAMSIC to verify whether it's correct or not, right? So the, how you call it, the RAMSIC is more like a verification of this map. On the QTL. But- Oh, see, it's all-
No, this is just
Oh.
GBS plus SSR.
See, another thing is, things right now, GBS, so SSR with GBS compared to SSR with RAMSIC, which one you would like? I mean, in this population, I understand that RAMSIC, the coverage might not be that well, especially.
I like RAMSEQ markers because they're more informative than GBS markers.
So that's another thing, but then, okay, for the RAMSIC marker with SSR, can we still use the same set of, I call it the format or script?
Yeah.
That's the same.
This runs anything that comes out of LabMap.
Good. So that's a good thing. Yeah, so that's another thing is instead of SSR with, but then the coverage on this one, I mean, SSR plus the GBS,
Mhm.
the SSR still have a high number with the GBS.
A pretty high number,
Right.
yeah. Some of them get
Right.
filtered out because they distort
Right,
stuff,
right.
but we
That's
still
okay.
have over 350
But
probably.
compared to the, well, if we want to do SSR with RAMSIC, how much of that?
I've only
How many
ran.
of the SSR might you kick out?
Yeah, I've only ran a few of the RAMSEQ plus SSR maps, and it's been a while. I'll be doing that probably shortly for the CHCS population. But it just depends on how well things are genotyped, kind of.
How many patient population you are able to
From this
from
population.
the
from the
SSR for the Norton population?
For the Norton population, I think I have all but like maybe 10 different
Oh,
markers or something.
But CHCS is more.
Yeah,
Oh, okay.
CHCS, we have more missing. Most of them are those markers from,
So what kind of a possibility that caused this? Because again, well, correct me if I'm wrong, okay? The sequence position is reflect to the Pinot Noir sequence, right?
Yeah.
Genome sequence. So are you telling me the Norton sequence better fit the Pinot Noir sequence than Chamberset?
no, what I'm saying is like the files that I have, because there isn't just one place where you can find the physical positions of all of the SSR markers. Genoscope has a lot of them, and CBI has a lot of them, but some of them, I think, is it the UC Davis ones that are like the CTG?
So you mean.
All the
some-
papers refer to a website that doesn't exist anymore, and you have to look up the primer codes in like BLAST, and it just takes a while.
Takes a lot of time.
And I had to do that for maybe like 40 or 50 markers for the Norton by Cab population, but I did it and I found them and that's done.
Still there.
Yeah, and it works to do it through the BLAST. It just takes a while.
Use the primer, lots of the primer
Yeah.
and to find the patient population.
Mhm.
But did they show what kind of crop or something they found on the primer or?
Oh, I use the Vetus
Okay, okay.
genome for those blasts.
Yeah, some of the website just already put down some information just because.
Yeah, it's just kind of annoying. And I think there's more of them in the CHCS genotype file, but I've also included more of those markers that we don't actually have like good genotypes. I'm considering like in that 150 or whatever that are missing still. I am including markers that we don't have like good genotypes for. So I'm not sure what the number is as far as mappable markers.
So is that really true now? Actually, if we combine SSR and REM-seq, that would be way better than SSR. CDS.
I don't know if I can say like way better. I haven't
Actually, just better.
I haven't handled them before, and I've never mapped any like traits on one of those maps. So I'm not sure, but theoretically, like I think it should be a good quality map. Obviously, we're probably only going to have like close to like 1900 or like 2000 markers on that map because I guess I'm not sure for CHCS, but we only get like 1400 RAMP-seq markers or 1500 that are actually good quality.
For the numbers roughly, if I filter, probably 1600.
Yeah.
Well, 1600 is still the best one.
Yeah.
Nobody work on that.
Yeah.
right?
Yeah.
So,
Yeah,
so
I
I'm
filtered,
thinking,
I kind of preliminary filter and then pretty decent, so 1600, I think it should be still good to start with.
see, because according to what Lance believed that the REM-seq is the best SNP marker in the whole world.
They look like they map really nice by themselves. It does get a little more like jumbled up, so to speak, when you add the SSR markers, but I'm sure if you take out the problematic ones,
Should be okay.
it should be okay.
Yeah, see, because in this way, both SSI and REM-seq, they are transferable from one thing. By the second thing, I just don't know. Okay. What was it from?
But both of them are multi-allelic, which I think
Right.
is more informative than the
Right.
GBS, which is more informative than the
Yes,
GBS.
so, yeah.
So you mean from here, line 129, you just after the plot, you just manually change the.
Yeah, I take out the FE or I add it back. That's all you have to do.
It just make, just manually change it.
Yeah, I can,
Yeah.
I'll make a note, but I can also do like 2 of them and comment one out, if that would be easier.
Yeah, I'm gonna ask you, think that would be those. Who will see them? You will see.
Okay.
Because the student needs to know all that.
So you try to 185?
Oh, this was what I added yesterday to your script. It just writes out this, it's called something different since I have added a few things, but this new map just contains the map information plus the physical positions.
So this is more comprehensive final copy for all the markers.
Yeah, it's what I use when I look at the map and I'm trying to like remove stuff. I've sorted this kind of funny, but for example, if this was actually chromosome 2 and these markers had sorted to the wrong group, I could highlight these names and then take them out of the VCF file later. Okay, so that's converting all of the genotype stuff, I believe. And this is the second part, which you don't have. So we'll just kind of go over this briefly because I doubt a lot of it'll make a lot of sense. But this is adding the phenotypes to that genotype file. And we read back in the files instead of continuing with the objects
So
from
the
above.
pedigree is different from the top.
No, it's not. I just reread them in case you want to run this separately from the top. Okay, so the pedigree file just has the population information, which is important. I guess I should change this in my instructions. It looks like I've changed it to be a lowercase p that it looks for, which I could actually Now it shouldn't matter, but it's reading in the phenotype file and it distinguishes the phenotype file from the other files because it has pheno in the name. And like the VCF file, there should only be one phenotype file in your folder that you're working in.
Phenotype of which you need to convert into the CBS file.
CSV. I think, yes, it should be a CSV file. That's a good, I just work in CSV files, so I kind of forget that sometimes. I'll add a note. Generally speaking, it's easier to handle CSV files in R. So that's kind of like the default over actual Excel, but CSV files open in Excel, so it's not hard to just work in CSVs.
So when you start work on reading, you cannot put the phenotype.
You could have an original phenotype file in an Excel and then just save it as CSV.
But then folder you cannot load there because you can allow one. We see it.
One pheno file? Yeah, you should just have. No, there can be lots of CSV files because it's identifying which one's the phenotype file from the pheno in the name. If you want to have two phenotype files in that folder, the second one just can't have pheno in the name. And maybe, let's see, maybe it'll make sense if I show you how this works. Okay, so this list files function is it lists all the files at a given location. And so if we do the list files for our path, which is our file that or folder that we're working in, it lists all the files that are contained within that folder. And so we have our phenotype file here, we have a hat map and a CSV, and then we have the outputs from letmap and our pedigree file. Those are all the files that are contained within there. What the subsequent text does is it looks through this list of files and looks for the file that has the word pheno or the text pheno in it. And so if you have two files with pheno in it, it doesn't know which one to choose, which is why you need to just have one. Because if I run this, it'll tell us which number in this list is the pheno, which it will be 1, because it's the first position in the list. So then it can extract this file name.
File need to convert into the VCF.
No.
Don't have to, text file should be fine.
The pheno file needs to be in CSV, not the VCF. Yeah.
I can use the Excel save that CSV.
Yeah. Exactly. And then it stores the name, this name, all monthly averages.pheno. It stores this name to this pheno.file object, and then we can read in this pheno.file object. And I just do that instead of defining a name, so then it works no matter what the name of the phenotype file is, as long as it has the word pheno in it. Okay, so then the phenotype file gets read in, and this is standardizing the names, because sometimes the names in the phenotype file will just be numbers for all of the like N cross C S individuals. Whereas the genotype file has like the CGB 11 or CGB, what is it, like 14 or whatever the other 9, whatever the other number is. We're just standardizing those so they're the same. And so we can compare between the geno and the pheno file. Let's see, that's what this is doing. It's assigning, this is also standardizing the genotype names, because in some of the genotype files, we have CGB 11, CGB 011, CGB 2011 in the names, and it's converting all of those just to CGB 11. Additionally,
So I can just change this. Share 14 and 16 for the changes.
Oh, those won't be an issue. It's just the header or the prelim. I'm just standardizing it because that's how it.
I think that one also had this kind of issue. because-
Yeah, but what this does, it has like the header part of the genotype name, and then it has the actual number part. In my script, I'm pretty sure I like separate those, and then the number part gets stored as a number. So then those zeros get dropped off the beginning ones anyway, so it's fine.
So for this one, if we Chambers and Cabernet Sauvignon, if we combine SSR with Ramsey and still have about 1,600 markers, that would be wonderful. The first phenotype we could do is powdery mildew. They already did 2 years. We
Mhm.
just need to get the second year data. But that's a good one. Okay, we could test with the.
Which I think, now that we're
See,
discussing
see,
it,
The Chambers are now actually, well, actually, the performance in state of Missouri for powdery mildew resistance is not that great. I don't know what kind of genotype of powdery mildew they get. So we'll see that. So that's immediately one we can work on.
sorry, I was just making a note for myself, because right now this is formatted for the N-cross-CS population. Like, I don't think the CGB 11 is a header.
No.
That's a part of the CHCS stuff. And additionally, in the Norton Cross Cabernet Sauvignon, the numbers like, what is it, 101 through like 119 or something are actually stored as a second version of like 1 through 19.
Yeah,
Yeah, it reformats those
okay.
as well, which we don't need to do in the CHCS. So I was just making a note to myself to fix it so it works through CHCS as well. That's all that's doing. This is replacing some of the numeric.
For the Chambers, I remember yesterday I told you they had the 99,
Mhm,
98 with a 0
mhm.
compared to 1 to 97 without copying issues because name.
No.
As long as they match, they should take it.
Yeah, as long as the like header information is kind of standardized in the names, I can tell the difference, or I can make or be able to tell the difference between header information and marker or individual number.
So as long as they are mentioned, they should be.
Yeah, this should be
That's
fine.
all of three. This one is just because you.
This is just because in some genotype files, like there just wasn't a standard like header information in the markers for Norton Cross Cabernet Sauvignon. In some of the files, it was only CGB 11, but some of them had CGB 011, some of them had CGB 2011, and it makes identifying that like header information difficult if they're not all like standardized. So I'm just standardizing them. Okay, let's see. This is replacing the numerical numbers in the phenotype file, because most of the time the individuals in the phenotype file are just listed like 1 through 250 or whatever. It doesn't have the like header part of the individual name like the genotype file does. So I'm just making those match in this stage. This is reducing the phenotypes. If reduces phenotypes to include only. This is reducing the phenotypes. I think I have a mistype in here somewhere. But if it's not in, I believe, the genotype file, then we're going to remove it from the phenotype file so that those two file types match. This is, we had previously saved our genotyping information that came out of LetMap as this file name. It's just reading that in. It's just reading that in so we can concatenate it with the phenotype files in some later steps, and it's just formatting it a little bit to take off the first column and make sure it's a data frame. These steps are matching the phenotypes and the genotype numbers. So if there's a phenotype that's not, if there's an individual that has a phenotype, but it doesn't have genotypes, we're going to remove those from the phenotype file. Likewise, if there's a genotype that doesn't have a phenotype, we're going to remove those from the genotype list. Let's see, phenotypes. These are, again, just matching. A lot of this stuff is just matching it up so that the phenotype column is exactly the same as the genotype column as far as individuals being in the same rows. This has, right here, there's this one line at 250 that's commented out. I've made different versions of this if you want to use the male map or the female map. If it's a consensus map, doesn't matter, you can just leave it how it is. But if you want to just use the male map for some reason, you could comment out this row and then uncomment this row and use that. And it's just because for the female map, we use columns 1, 2, and 4, but for the male map, we would want to use columns 1, 2, and 3. This step finally is attaching the phenotype columns to the genotype columns now that they have been all matched up. And finally, we can write that file to a CSV file. And then the last step with that in this RQTL file, I think it's going to be not the same. I think I've already edited it, but I have a note down here. Oh, sorry. That you must go to the CSV file and there's a series of like NAs in the top left corner. Those have to be deleted before it can be used as an RQTL CSV file. The NAs are needed in that file still for the missing like genotype or missing phenotype information, but they're not needed in the top left corner, and there's no way to remove them in R because an NA is data that has been removed, but when you write it, it saves it as the actual text NA. I'll show you.
The first three columns.
Yeah. Can I zoom in on this? This is what I mean. These first two rows, they have NAs in them, but they need to not have NAs in them. So just once you've ran that script, you need to come in here and delete them. You see right here, we start off with the marker number in this column S, and then there is the mapping actual information over here, the mapping information. Preceding that, within the phenotype information, which is what this is cold hardy data, so it just has the month names. We just need to delete all of those and save it again. And that's all you have to do, and then it'll run in RQTL. We just can't delete all of the NAs because we still need them in these locations. And that's a script. That's all you have to do. It seems like a lot when I like explained it all, but all anybody has to do is highlight this and click Control Enter, and it should go if you've set your path to the correct file. I think it's about 10 o'clock now, so that might be all we get done for this week.
So one last one, right, next week?
Yeah.
So we'll make it 10 weeks. Thank you so much, Joe.
Not a problem.
You really spend a lot of